In a similar fashion, the small amounts of thrombin, 2A, initially produced activates plasma factor VIII to factor VIIIa, simultaneously releasing the factor VIII from its plasma transporter, the large von Willebrand factor, VWF. Platelet membrane-bound factor VIIIa accumulates factor IXA, produced by the TF factor VIIa complex to form the intrinsic factor Xa. This complex is 6 orders of magnitude more active than factor IXA in factor X activation. It rapidly activates more factor X to factor Xa. The factor VIIIa-9A complex is 50-fold more efficient for factor Xa activation than the tissue factor VIIa complex, which is downregulated by TFPI, and the factor VIIIa-9A complex assumes the major role in factor Xa generation. Some of the factor VIIIa after activation cleavages spontaneously loses a peptide fragment which corresponds to the A2 domain prior to forming the complex with factor IXA. This dissociation process leads to inactivation of those factor VIIIa molecules. Prothrombinase, 5A10A, and the intrinsic factor Xase, 8A9A, are protected from inhibition by antithrombin and other plasma inhibitors when in the complexed form. Throughout this process, anticoagulant reactions compete with the procoagulant reactions to produce a threshold-limited reaction system such that the intensity of the stimulus must be sufficient to provoke a full-blown procoagulant response. The thrombin initially produced may also bind to vascular thrombomodulin, TM, constitutively present on the vascular endothelial cell, and activates protein C to activated protein C, APC. This enzyme downregulates the reaction by competitively binding and cleaving the 2 active cofactors in their respective A2 regions, leading to inactivation of the intrinsic factor Xase, 8A9A, and prothrombinase, 5A10A complexes. If the pathologic stimulus is sufficient to overcome the stoichiometric and dynamic inhibitory systems, the reaction will proceed with thrombin continuing to produce its activation products. Factor 13, the precursor to the transglutaminase factor 13A, and fibrinogen are cleaved by the small amounts of thrombin initially produced. The products of fibrinogen cleavage by thrombin begin to be observed when less than 0.2% of the total thrombin, 2A, to be ultimately accumulated is produced. Fibrin polymerization resulting in a visible clot occurs when approximately 35% of the A peptides and 10 to 15% of the B peptides are released. The factor 13A cross-linking process occurs coincidentally with this initial fibrin formation. The aggregated platelets and fibrin resulting from thrombin formation are the principal components of initial vascular plug formation and now provide the engine which achieves hemostasis. When a sufficient stimulus overcomes the synergistic inhibitor threshold, the accumulating mass of activated platelets will support increasing intrinsic factor Xase, 8A9A, and prothrombinase, 5A10A formation on their surfaces at specific platelet receptors and overwhelm the available local inhibitor concentration. These platelet-bound procoagulant catalysts execute the propagation phase of the reaction, during which massive amounts of thrombin are produced efficiently and continuously as long as more blood enters the wound site, adding more platelets and resupplying the plasma procoagulant catalytic process. The propagation of thrombin generation continues to expand, now independent of the initially presented tissue factor, TF, as long as there is a continuous supply of blood through flow, delivering new plasma procoagulant reactants, platelets, and fibrinogen into the site of perforation in the vascular endothelium, leading to increased platelet and cross-linked fibrin accumulation. Once flow has ceased because of the formation of a dam, the overwhelming concentration of inhibitors present in blood, including TFPI, antithrombin, heparin cofactor 2, alpha-2 macroglobulin, and alpha-1 antitrypsin, inhibit the various reactants as they dissociate from their respective complexes. In the vasculature downstream from the growing thrombus, procoagulant enzymes and active cofactors escaping from the wound site are quenched rapidly under normal circumstances by the stoichiometric and dynamic inhibitory systems of blood in cooperation with elements of the vascular endothelium. TFPI inhibits the tissue factor, factor 7A, factor 10A product complex. Thrombin 2A binds to resident thrombomodulin molecules constitutively present on the vascular endothelial cells. The resulting complex, TM2A, activates protein C to APC, which in turn downregulates any intrinsic factor 10As, 8A, 9A. The free serine proteases, 2A, 9A, 10A, of the coagulation system in the plasma environment are rapidly inhibited by the surplus of antithrombin AT molecules. This reaction is significantly accelerated by the interaction of antithrombin AT with heparin sulfate proteoglycans, HSP, presented constitutively on the surface of the vascular endothelial cells. When operating properly, this system of blood leakage attenuation, known as hemostasis, displays the appropriate level of procoagulant required to obstruct blood loss, relevant to the vascular insult, but is precluded from systemic activation of the coagulation system. The terms initiation, propagation, and termination are selected for the semantic description of intellectually separable events during the blood coagulation process. The presentations associated with these three processes, however, are ongoing continuously in the phenomenon of hemostasis. These intellectually separable events can be further subdivided into the particular reaction sequences and can be identified mechanistically as contributing to the overall process. In reality, however, each of these sub-events and major events of the coagulation system with which they are associated part of an ongoing continuum in which initiation, propagation, and termination reactions occurring in an almost simultaneous collage of events leading to clot formation or elimination of clot-forming activities.